In this video, we're going to continue kind of looking at vector spaces and subspaces, and now that we understand that this idea of a vector space and subspaces within a vector space give us a structure of the objects we're looking at, now we want to kind of refine our understanding of that structure and basically see how all the vectors within a vector space or a subspace interact with each other. And before we get there, one quick little review of something we mentioned at some point earlier in the semester, I can't remember when, the idea of a linear combination. And I'm not going to write the incredibly long wordy definition of this, but if we recall, essentially the idea is if I have a vector v, if I can write it as c1u1 plus c2u2 plus all the way up to ck where the u sub i's are vectors and the c sub i's are real numbers, scalars, then I can say that I can write the vector v as a linear combination of the vectors u sub 1 through u sub k. And we did this earlier, and we'll do maybe one example as we go through this, but this idea of creating a linear combination and finding these c sub i's is important, but we already went over that earlier in the semester. We already have the algebraic trick, setting up a system of equations, solving it all out to get the c sub i's. We'll do it, I think, for one of them, just to make sure we're all clear on it. But just be aware, that thing we did earlier, you need to know how to do it here. It's the same algebra over and over, so it shouldn't be that big of a deal. But the idea is, first we want to look at what's called a spanning set. And we can say this. Let S equal the set B1, B2, all the way up to VK. Be a subset of a vector space. Like I said before, I'm just going to use VS for vector space, of a vector space V. The set S is a spanning set of V when every vector in V can be written as a linear combination of vectors in S. And the actual notation for this, we say span of S. There's different ways to write it, but that's actually the way I'm going to write it. I'll use that notation. There's a few other ways to write it. And again, as far as kind of the different terminology and the way we say things here, if the span of S is equal to V, then the way we actually say it is S spans V. So the idea is we have a vector space, and then that vector space is composed of a bunch of vectors. So then we take a subset of V, some of the vectors, and then we look at all the linear combinations we can create from those vectors. That's called the span of S. And the question then becomes, does the span of S encompass all of V or just some of V? One thing to point out, and we'll kind of mess with this a little bit later, this set S is a subset, not a subspace. We'll see later on when it is, what it is, things like that. But for right now, this is not a subspace, this is a subset. We have a collection of vectors in our vector space V. I take a bunch of them, some of them, however many I want, and then I look at this thing's span of S, which is all the vectors in S and all the linear combinations I can generate from S using this thing right here. That set I call the span of S. And then essentially my question is, does my span of S encompass all of V or just part of V? So really quickly, just a couple of examples. Here we'll stick in R2 for both of these. So my first set S, we'll say S sub 1, will be the set of vectors 0, 1, and 1, 0. And the question is, if I have that set S sub 1, what is the span of S sub 1? But if you think about it, in this case, for any vector in R2, let's see, let U sub 1, we'll write it this way, U sub 1, U sub 2 be an element of R2. So suppose I have some arbitrary vector, I said vector and I wrote set notation. Lots of different notations here, and I have to try to keep them all straight, is that right? Let U sub 1, U sub 2 be an element of R2, an arbitrary vector. But, well, let's see. If these are my sets S sub 1, if I just multiply, let's see, if I let C sub 1 equal U sub 1, C sub 2 equal U sub 2, then U sub 1, U sub 2 is just equal to U sub 1 times 1, 0 plus U sub 2, C sub 2 times 0, 1. Because then if I multiply these out, I'll get C sub 1, 0 plus 0, C sub 2, which will give me the vector C sub 1, C sub 2, but this C sub 1 and C sub 2 is just U sub 1 and U sub 2, so they're equal. Which means any vector in R2, I can write as a linear combination of those two vectors right there. Which means the span of S is all of R2. So in this case, S sub 1 spans R2. Suppose we have something else. Let's see. Let S sub 2 equal the set 1, 2, and 2, 4. Those two vectors. Well, let V sub 1, or let's say V, let V equal the vector 3, 5. These are certainly in R sub 2 again. 3, 5 is definitely a vector in R2. Using these two vectors, as opposed to these two, which span all of R2, can I write V as a linear combination of those two vectors? Again, here's where I just want to run through the trick. So we set it up like I did there. 3, 5 equals C sub 1 times 1, 2 plus C sub 2 times 2, 4. And now if I solve this out, 3, 5 is equal to C1, 2C1 plus 2C2, 4C2. If I then write out my system here and equate first to second, I get 3 equals C1 plus 2C2. 5 equals 2C1 plus 4C2. But now, just to save time and not write out all the matrix formulation here, multiply the first equation by 2. And I get 6 equals 2C1 plus 4C2. 5 equals 2C1 plus 4C2. And now clearly there's not going to be any solution there that will actually work. I could do it by way of matrices, but I can see it right here obviously. Which means, in this case, this can't be written as a linear combination of those two vectors right there. Which means, again, to get an idea of what we're going for here, what this is really telling me is, I have a vector space, say R2. I can pick some vectors in R2. I pick these two, I pick those two. Then I look at the span of all of the span of the set that I generate, S sub 1 or S sub 2. Sometimes that span will give me the entire vector space. Other times, it clearly won't, because there's a vector in R2 that isn't in the span of that, because I can't write it as a linear combination. And the question becomes, what does that mean? Does it mean anything? Is it important that maybe this spans R2, but that doesn't span R2? What does it say about the structure of the vector space or of the elements of these sets? That's actually what we care about. Okay? So, we get to go through a bunch of different theorems and corollaries and definitions today, but I want to at least make sure you get an idea of what we're talking about. So, theorem. If S is equal to V sub 1 through V sub k, and at this point, we're going to keep on using this general S for my set S that I'm going to use and then span. I might get tired of writing that, so I might just write S, and we'll assume this right here is a set of vectors in the vector space V. Then the span of S is a subspace of V, and the span of S is the smallest subspace of V that contains S. So again, understand the difference between this, which is a set or a subset of these vectors, and now we're showing that the span of S is a subspace of V. As far as a proof goes here, there's really two things we want to do. One, we need to show it's a subspace, and then two, we need to show that the span is the smallest subspace of V that contains S. This second part is actually a homework exercise. I think I assigned it to you, but I may not have. But that's a homework exercise, so I don't want to prove that. You can do it on your own. The first part is actually pretty straightforward. We understand now, in order to show that something is a subspace, I have to show it's closed under addition and scalar multiplication. But if I take a couple of vectors in this set S, and then let's see, I need to show it's the span of S is linear combinations of those vectors right there. So maybe the vector, I'll use W. One vector in the span of S is W1, which is equal to C1 V1 all the way out to CK VK. Another vector, W2, is C1 V1 out to CK VK. And here, these C's don't have to be the same, so maybe I'll just put bars over them. But I have two vectors that can be written as a linear combination of the vectors in S, which means they're in the span of S, which is what I care about. To show it's closed, I have to show the sum of these is in the span of S. But clearly, if I add these together, I'm just going to get C1 plus C1 hat V1, etc., 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 which will be a linear combination of these V sub i's, which will put it in the span of S. By the same token, if I multiply one of these by a scalar, it's still going to be a linear combination of the v sub i's, so it's going to be in the span of S. Also, while we don't have to show it as long as we have our closure, we know we need to have a 0 in there, but if I make all the c sub i's 0, I get my 0. So it's easy to see that all the properties of a subspace are followed by the span of S, and we can get that it's a subspace. Okay, good. How far are we along? I might need multiple videos for this. I don't know. Well, okay. More definitions. Really important ones. Here, again, I don't want to do a lot of these, so this one I'm just going to assume and let you do the math on your own if you want. Suppose I have this S. Here we're going to use a different one. 0, 1, 2, 1, 0, negative 5. Suppose that's my S right here. Now suppose I generate this equation. C1, V1 plus C2, V2 plus C3, V3 equals 0. Where V sub 1 is this, V sub 2 is that, and V sub 3 is that. And the question is, if I write this equation right here, how many solutions are there? Or can I find any solutions? Right away, for this and for any equation of this form, we recall from earlier, this is homogeneous, we get the trivial solution. If c sub I is equal to 0 for all I, it works, which is just the trivial solution. And that will be true for all of these. Are there any other solutions? Well, in this case, and here again, I'm going to skip the algebra, but so you'll just have to trust me on this, or do the math out yourself. If c sub 1 is 1, c sub 2 is negative 3, and c sub 3 is negative 1, it works. So now I get a non-trivial solution. What does that mean? If we look at one other really quickly, suppose S is equal to 0, 1. Actually, I'm going to be orderly here. My brain doesn't like this. 1, 0, and 0, 1. So now I look at c sub 1, v sub 1, plus c sub 2, v sub 2 equals 0. Clearly, if c sub 1 equals c sub 2 equals 0, it works. Are there any other solutions? Well, let's see. If I just plug in c sub 1 times 1, 0 plus c sub 2 times 0, 1 has to equal 0, which is, in this case, 0, 0 in R2. But then I get, if I multiply in and then combine, c sub 1, c sub 2 equals 0, 0, which then implies that c sub 1 equals c sub 2 equals 0. Which means the only solution here that will work is if the c sub i's equals 0. So now, apparently, sometimes, if I have a subset, this equation will always have the trivial solution and also have non-trivial solutions. Other times, the only solution I'll get is the trivial solution. And again, from a math perspective, the question is, does it mean anything? What does it mean? We recall from earlier, this one also has the property that the span of S equals V, where my V here was R2. So again, now you kind of start mixing things up from a math perspective and say, hey, if I have vectors and the span of those vectors is the entire vector space, is it always true that this equation right here will only have a trivial solution? Or put another way, if these vectors here give me a non-trivial solution, does that mean, and I'm not going to do the work here, but you can, does that mean if I look at the span of these vectors, they won't be my entire vector space? In this case, this would be in R3. And maybe there's some type of connection between what the span gives us and the solutions to this equation. And again, we're still working on that, but from a math perspective, that's kind of how you look at things. You say, maybe there's something going on here. And then you mess around with it, which is what we're going to do. So let's see, a definition. A set of vectors S equal to our standard v1, v sub 2, up to v sub k, in a vector space V is linearly independent when C sub 1 v sub 1 plus C sub 2 v sub 2 all the way up to C sub k v sub k equals 0 only has the trivial solution C sub I equals 0 for all I. Otherwise, it is linearly dependent. And I will also point out right here before we work with this, this is actually how a lot of independence it's a standard math thing in a lot of different areas of math, independence and dependence, and they all more or less are based on the same idea. And generally speaking, the way you define dependence is by saying not independent. So you'll have a definition for independence, which is what we have here, and then you say, if it's not independent, then it's dependent. So the definition of dependence is essentially that it's not independent. There's other ways to do this based off of this definition right here, which we'll see. But another way of saying it is it's dependent if it's not independent. Okay. So, going back to what we just said earlier, if we go back to R2, if I have S sub 1 equal to 1, 0, 0, 1, I know that this equation with those vectors will only have the trivial solution. That means it's linearly independent. Suppose I have S sub 2 equal to 1, 2, and 2, 4. Would that be linearly independent or dependent? Well, I guess we can try to check it really fast. I had wanted to not check all of these, but whatever. So we have, let's see, 0, 0 is equal to C sub 1 times 1, 2 plus C sub 2 times 2, 4 equals C sub 1, 2C sub 1 plus 2C sub 2, 4C sub 2. Then if I write this as a system of equations, 0 is equal to C sub 1 plus 2C sub 2. That's the first component. 0 equals 2C sub 1 plus 4C sub 2. But now, if I just look at the first equation, c sub 1 is negative 2c sub 2. And then I can plug in down here, and I can find a solution. 0 equals 2 negative 2c sub 2 plus 4c sub 2. 0 equals negative 4c sub 2 plus 4c sub 2, which is equal to 0, which tells me any c sub 2 I plug in will work, and if any c sub 2 I plug in works, then by extension any c sub 1 I plug in will work. Which means this actually has infinitely many solutions. And yes, I am doing this rather briefly with a system of equations. You can also do it in matrix form. But that means I can get a whole lot of solutions to this, which means this is linearly dependent. Which then again begs the question, is there something going on here? More to the point, if I know these are linearly dependent, which means this has more solutions than just the trivial solution, what would the span of this be? Would it be all of R2? Actually, no, because this is the one we started with. And we saw that this couldn't generate 3, 5. Which means now we begin to see a connection. These vectors span my entire vector space R2, and they're linearly independent. These vectors do not span all of R2, and they're linearly dependent. And maybe we begin to see a connection. Okay, theorem time. A set S equal to, like I said, V1 to Vk with k greater than or equal to 2 is linearly dependent if and only if at least one of the V sub I can be written as a linear combination of the other vectors in S. And the proof of this is actually not all that challenging, but we can see it here. This is an if and only if, which means I have to go both directions. But just looking at this right here, these are linearly dependent, which we saw, and clearly either one of these can be written as a linear combination of the other one, just multiplied by the appropriate constant, 2 or 1/2. So that's easy enough to see. And if I go in the other direction, if I assume one of these can be written as a combination of the other, then it's going to be linearly dependent. All you have to do to prove this in general is just write out an arbitrary system of equations, C1, V1, out to CK, VK equals 0, etc., etc., and do the exact same thing. Rather than looking at a specific example, do this. I don't want to run through it because this video is long enough, and we already did it in a specific case here. But yes, the algebra is not all that challenging, so I would encourage you to do that one on your own. And again, we see this connection between, well, these are linearly independent. Clearly, I can't write one as a combination of the other. These are dependent. I can write them at one as a linear combination of the other, and you can expand on this to more vectors, like up to an arbitrary k. And this is in some way telling me something about what those vectors will span. Whether I'll span the whole space or just part of the space. one last thing, and then a few kind of final thoughts. Two vectors u and v in the vector space V are linearly dependent if and only if one is a scalar multiple of the other. And again, this is really just a corollary of the previous theorem, and it is actually exactly what we saw with the S we had that was linearly independent. 1, 2, and 2, 4. One is a scalar multiple of the other. So this is straightforward, not worth even proving out or worrying about. But the last few things to think about now, and again, kind of the math way of looking at this, assuming I didn't actually know everything we're going to cover in the rest of this book. From a math perspective, you would maybe say, well, okay, so I can write some arbitrary vectors. I'll just make some up in R2. There's some right there. With those vectors right there, I could then look at the span of those vectors and see if the span gave me all of R2 or not. I could certainly set up the equations and go from there. I'm willing to bet, looking at these, given that none of them appear to be multiples of another, that you might be able to pull it off there. But then from a math perspective, you say, okay, are these vectors linearly independent? Well, now I have a way to show that. I can set up my system of equations and check it to see if I get the trivial solution or other solutions. There's other things we've looked at that would maybe save you some time with that. If these are all linearly independent, can I maybe, and they span all of R2, can I maybe remove one of them arbitrarily? Could I remove that? Would they still be linearly independent? Would they still span R2? If, for the sake of argument, again, I'm just making these up. So off the top of my head, I don't know if they'll span what they span, blah, 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 but we're just saying. If they don't span all of R2, can I maybe add a vector to them that will make them span all of R2 to kind of collect up anything I'm missing? Because it would seem that there seems to be some connection between linear independence and dependence, and spanning a whole vector space and not spanning a whole vector space. And let's face it, if I want a nice way to describe a vector space, simply looking at the vectors that span it is a nice way to do it. I can talk about R2, or I can say, look at the set 1, 0, 0, 1, which spans R2. So maybe, given arbitrary vectors, I want to find a set that will span the entire vector space. Can I add vectors to a vector space, to a subset, so that it will span the whole vector space? Can I take some away so I can kind of find the smallest way to do it? I mean, clearly here, if I added 1, 0, and 0, 1, now I know this will span all of R2, because by themselves these do. But do I have to add those? Do these do it by themselves? These are all the types of questions we ask from a math perspective. I would also point out, given that I know a bunch of you are engineering people, which means you probably think more visually than I do, maybe think about it visually. If you think about it in terms of R2, the vector 1, 0 is this one. The vector 0, 1 is that one. Hey, they're orthogonal. And apparently they're linearly independent, and they span all of R2, which makes sense. I can use multiples of this to go left and right wherever I want. I can use multiples of this to go up and down wherever I want. If my two vectors were, say, 0, 1, and I know this will be messy, but 0, 1, I'll draw it next to it, 0, 2, and those were the only two I had, I can certainly go up and down, but I can never go left and right. These are multiples of one another, they're dependent, and they don't span all of R2, because I'm only really getting one direction, if you will, and I need two in R2. If you wanted to look at R3, you'd be looking at multiple planes. If those planes are orthogonal to each other, then you can kind of shift anywhere you want in R3 by going this far in one plane, this far in another plane, this far in the third plane, and getting to where you want. If your planes are parallel to another, multiples of one another, then essentially I'm going to miss out on a direction. If I want to span the whole set, I'm going to have to add a plane that's orthogonal to the ones I have. So there's the algebraic way of looking at this linear algebra. There's our algebraic definitions, and then again, if it helps, if you think visually, think about what these vectors are doing. If they're orthogonal, we haven't actually proved this yet, but if they're orthogonal, it would appear that makes them linearly independent, which is helping them span the whole set, the whole vector space. If they're dependent, they're multiples of one another, which means they're not orthogonal, which means logically they can't generate the whole set because you're missing out the whole space, because you're missing out on stuff. We will formalize this more in the next video, which we'll get to next week, but just kind of keep pondering this after you finish your exam. There is a structure here that we're trying to kind of develop and see, and you can think about it algebraically, or you can think about it graphically, geometrically, and kind of see where they connect.